Hello and welcome to Unit 1, Lecture A. Today we are going to be talking about properties of matter and energy. In science, one of the first things that we have to talk about is what units we're going to use, and we're not going to use the English measuring system. We're going to use the metric measuring system. It's also called the International System. They usually call it the SI system because it's System International. If you want to know what those units are, reference table D has them listed for you. Okay, so measurements, table D, mass is an amount of matter in a sample. It is different than weight. Weight is a measure of force pulling on that amount of matter. Mass is how much stuff is really there. The biggest difference, if you went to the moon and you took your mass, you should have the same amount of matter in you as you did here on Earth, so your mass will be the same, but gravity pulls on you less on the moon, so your weight will be much lower. You will see mass and weight kind of used interchangeably in chemistry, but next year when you take physics, you're going to have to make sure you get it right. Length, the difference between 2 points. Time, what happens between two events. Time's kind of hard to define, but that's typically how they try to define it. Volume is how much space an object takes up. When we're finding volume of a liquid, we use a graduated cylinder. When we're finding volume of a solid, we tend to use cubic centimeters. And remember that with water displacement, 1 cubic centimeter has the same volume as 1 milliliter. That lets us do the water displacement thing. You learned about that in earth science. Density is a derived unit. Whenever we say something is a derived unit, that means it's calculated. We don't have a piece of equipment that measures density directly. We have to find something's mass and something's volume and then calculate its density from that. So density is a derived unit, and the equation for that is on reference table T. One of the really important measurements that we're going to use a lot is something's temperature. Temperature and heat are related, but they're not the same thing. Temperature is an arbitrary scale. You can make up any temperature scale you want, but the temperature itself is a made-up value. It doesn't actually exist. You can't actually hold a Celsius in your hand. You can't feel a Celsius. The energy itself is measured in joules. Okay, so we saw that on table D, energies in joules. Temperature is the average kinetic energy in a sample. This definition becomes really important because if a test question says you have these two samples, which has the highest average kinetic energy, you're basically looking for the highest temperature. So whenever you see average kinetic energy in a test question, I want you to write above it temperature because they are the same thing. Average kinetic energy, temperature. So kinetic energy is the energy of motion. It's how much the particles are moving. Everything is moving all of the time. We don't feel it because it's a matter of scale. We're very large compared to the tiny size of these atoms and molecules, so we can't feel them moving and shaking, but they are. The average amount that they're shaking is something's temperature. So we have the Celsius scale, which is based on water. The Celsius scale was based on the temperatures that water boil and freeze at. So they took the boiling point and on their little thermometer they marked it. They waited and put the thermometer into their water sample. When it froze, they marked that. And then they divided this up into 100 equal degrees. So our freezing point for water in degrees Celsius is 0, and the boiling point is 100. Okay, so there's a change from that point to that point of 100 degrees. Having a temperature scale based on water becomes really, really helpful for chemistry because most of our chemistry is going to be done in aqueous solutions. Aqueous water. and they'll abbreviate that AQ. The Kelvin scale, on the other hand, is based on this concept called absolute zero. So Lord Kelvin decided, he was a physicist and a very brilliant mathematician, and he said, well, if temperature is this average kinetic energy, then when the particles stop moving, that would be the coldest you could really get, so that should be your zero mark. So even when something's cold, if something's negative 10 degrees Celsius, the particles are still moving, they're still shaking, and so you have all these negative numbers to your temperature scale. But with absolute zero, Lord Kelvin said when the particles aren't moving at all, that's the coldest you could get, that should be your zero. So he made that his zero. He made a Kelvin, and notice there's no degree there. He named them after himself, and he didn't make them degrees, he just called them kelvins. So a Kelvin is equal to 1 degree Celsius. This way our scales match up. So the freezing point in Kelvin is going to be 273, and the boiling point of water in Kelvin 373, and that's still a change of 100 kelvins. This makes our conversions easy. All you have to do is add or subtract 273. So there's the equation here. And if we look at reference table T, we have our density equation. Remember I said that was on table T right there. Density equals mass over volume. And right down here at the bottom, here's your temperature change. Kelvins equals degrees Celsius plus 273. So we're going to use the Kelvin scale for a lot of our math work, because with no negative numbers, you don't have to worry about temperature being in the denominator of any of your equations. All right, so if we're doing a conversion, the example here, the temperature outside is 28 degrees Celsius. What's the temperature in kelvins? You just plug 28 in. So kelvins is 28 plus 273, and then you have 301 kelvins. Easy enough. Fixed points on a thermometer, you should know those in degrees Celsius and Kelvin. Absolute zero, lowest possible temperature where the motion stops. And then here, of course, is a scale showing you that from one point to the other, a Kelvin is the same size as a degree Celsius. Now I have the Fahrenheit scale on here just so you can compare 32 to 212. That's a change of 180 degrees Fahrenheit. So Fahrenheits are smaller than either a Celsius or a Kelvin, but a Kelvin is equal to a degree Celsius. A Celsius is greater than a Fahrenheit. Moving on from temperature then, we're going to talk about energy. So temperature was that arbitrary scale, and energy is going to be the actual thing itself. One of the first things that I want to say, and you're not going to believe me, and it's going to be one of the things you have to be careful of, there is no such thing as cold energy. No cold energy. No negative energy. Everything exists. This is why we have the Kelvin scale. When you put something in your refrigerator doesn't make it cold. It takes the heat out of your food. So it doesn't give cold to your food. It takes heat away from your food. Heat is like cookies. There are no negative cookies. You can owe somebody a cookie. It can be a cookie you don't like the taste of, but you can't hold a negative cookie or a negative gummy bear or a negative apple in your hand. So the energy unit we're going to use is the joule. Look at how it's spelled. It's not spelled like a piece of jewelry. Joules, capital J for your abbreviation. It's a derived unit, so it's calculated. Heat is what we typically call the kind of energy that we find from the motion of particles. So heat is the type of energy that we measure when we are using our arbitrary temperature scales. So Your temperature scale is a way for you to compare how much heat two things have. Something that has a higher temperature contains more heat than something with a lower temperature. So if you take a second and you touch your desk right now, if your desk feels cold, your desk has less heat than you do. It still has heat, but it has less than you do, so heat moves from your hand into the desk, and therefore it feels cold to you because it is colder than your hand, but it still has heat. It still has a temperature. If you touch your desk and your desk happens to be warm, so maybe your laptop was just sitting there or you had your arm on your desk, and you put your hand there and it feels warm, your desk has more heat than your hand, and heat will go from your desk into your hand. And that's going to continue until both your hand and your desk are at the same temperature. So energy gets transferred from the object that's hotter energy goes from high to low. From the object that's higher to the object that's lower. From the object that feels warmer to the object that feels colder. So if you put warm food into your refrigerator, the heat from your food goes into the air of your refrigerator. The heat from the air in your refrigerator goes into the Freon that's running through all of those tubes on the back of your refrigerator, if you've ever pulled one out to dust it off. And then the heat goes from all of those tubes into your room. So we move heat around. It doesn't disappear. Okay, the equations on table T, let's take a look at those. So find your reference table. And right down here, there's a box for heat. And I'm going to zoom in on that a little bit so you can see what I'm talking about, because this one becomes important. There are 3 different equations here for heat. And I want you to take a minute and label them. This first equation, Q equals MC delta T, or Q equals MCAT. This is the one we're going to use when we change the temperature of something. Now C is specific heat capacity. How much energy does it take to raise the temperature of 1 gram of your substance 1 degree Celsius? Measured in joules per gram degree Celsius. Joules per gram degree Celsius. Okay? The next equation on that list is Q equals mH sub F. This one we are going to use when something either melts or freezes. For melting or freezing. Okay, H sub F, heat of fusion. This is also a constant. Specific heat's a constant, heat of fusion's a constant, heat of vaporization is a constant. And heat of vaporization is used for exactly what it sounds like. For when we boil the substance or when we let that substance condense back down. Specific heat, heat of fusion, and heat of vaporization for water are going to be found on reference table B. So if you're using water, see table B. You might want to make a note to remind yourself that those constants are on reference table B. So let's take a look at that now. Heat of fusion, 334 joules per gram. Heat of vaporization, 2,260 joules per gram. Specific heat capacity, 4.18 joules per gram degree Kelvin. You can also use degree Celsius here because a Kelvin and a degree Celsius are the same size, so it will work. Water has a very high specific heat. That's a very large number. Metals tend to have specific heats in joules that are actually less than 1. That's why a metal will heat up really quickly when you put it on a flame, but it takes a long time for the water in the pot to boil. It's because water has a very high specific heat. Okay, we talked about the metric system in the intro unit, and we talked about the base units being meter, liter, and gram. Joules are also a base unit for the metric system, so we can talk about joules and kilojoules, and we can convert back and forth. So kilo being the prefix for 1,000, there are 1,000 joules in every 1 kilojoule. So if you want to know how many joules are equivalent to 23 kilojoules, remember king, hectares, duck, bits. If joule is one of your base units over here, from kilojoules to joules, that's going to be 1, 2, 3 places to the right. So 1, 2, 3 places to the right, it's 23,000 joules. If you want to go from joules to kilojoules, how many kilojoules are equivalent to 57 joules? We're going 1, 2, 3 places to the left. So this time you're going to have 1, 2, 3 places, 0.057 kilojoules. Now, a lot of times I'll put that extra 0 in the front so you can see where the decimal place is. Okay, two kinds of energy changes, exothermic and endothermic. In biology, you may have remembered talking about an exoskeleton and an endoskeleton. Insects have an exoskeleton. Their skeleton is on the outside. We have an endoskeleton. Our skeleton is on the inside. Exo means released. Exo means outside. So an exothermic reaction is releasing heat. So therm means heat. Exothermic, outside heat. So it's something that's going to release heat. So it's going to feel warmer. So if you put two chemicals together and it feels warmer, it's exothermic. Fire, a really good example of something that's exothermic. Reactions that give off light also are exothermic. Endo means inside or within. So endothermic are going to be heat within. Okay, so these are going to absorb heat. In exothermic, the chemical potential energy is turned into heat. In endothermic reactions, the heat is often turned into chemical bonds. These are a little bit harder to identify just in kind of common everyday things, but if you ever get one of those cold packs where you snap it and it gets cold, that's going to be an endothermic reaction. That equation, that MCAT, Q equals MC delta T. Here it is in your notes. I already showed it to you on table T. You're going to use this one when the temperature changes. Specific heat, remember, for water is on table B. Okay? You're just going to have to get used to mostly what the symbols are for the equation, so that when you read a word problem, you can pick out which letter each thing in the word problem represents. So this is something that we'll practice in class a little bit, and I'm just going to do one practice problem for you here, and then we'll wrap up for today. The question says, how many joules of heat, according to table T is Q, and so they want to know how many joules of those, so that's what we're going to be looking for, are absorbed when 30 grams of water, so grams are the unit that we use for mass, are heated from 30 to 35. So 30 to 35 is going to be a change in temperature of 5 degrees. And when I look at my equation, I have Q equals MC delta T. They want to know the Q, that's going to be my X. I have the mass, that's 30. C. C is specific heat. Specific heat is a constant, and what we need to know for C here is that it's water. So where do we go to find it? Oh, I remember specific heat is on reference table B. So here it is, 4.18. I can go back and fill that in. 4.18. And my change in temperature is 5. And now all you have to do is plug in the numbers and solve. And we have a heat of 627 joules. The questions get a little tricky when they're looking for the change in temperature. The way it's worded is a little different. When they give you the Q and they want to know the mass, sometimes that throws people off. So we're going to practice these in class and you'll get used to them. They're not scary, they're just word problems. Just know anytime that they're talking about a change in temperature, you're going to use this Q equals MC delta T equation. Okay, that wraps up today's lecture. And next class, we will talk about what matter is.